So we're going to do a quick walkthrough on the two practice exams. So question number one, acyl chlorides or acid chlorides have properties that are distinct from carboxylic acids. So we're going to name the following compound. A couple of things we want to keep in mind. We have stereochemistry. Both the hydroxyl group and the methyl group need to have assigned stereochemistry. Remember, we want to make sure that the lowest priority, in this case the hydrogen, which would be dashed, is dashed, which in this case it is for both. And then we're going to go through the process of assigning priority. So in this case, the hydroxyl is going to be our highest priority, then this bond, then this bond. So that goes 1, 2, 3. So the 2 compound here, right? And then if we think about it, we want to make sure that we've assigned this correctly. So let's take a look at this one. So my acid chloride has the highest priority. So 1, 2, 3. So that's counterclockwise. So that's the 3 carbon. That's going to be 1, 2, 3. So if we think about it, right, this assignment isn't quite right, is it? This should be S, and this should be 1, 2, 3, R. So let's flip-flop these. It should be, I see why. Let's take a look. This carbon should be my 1 carbon. This carbon is my 2 carbon. This carbon is my 3 carbon. So what I want you to notice here is, right, it really depends if you're numbering correctly. If you numbered this 1, 2, 3, you would be confused, right? Make sure that you're numbering this 1, 2, 3. Then your naming will be correct. And the rest of it you already know. This is 3-hydroxy, 2-methyl-butanoyl chloride. Notice for the acid chloride, it's OIL, and then chloride. So most important things here, make sure that your numbering is correct. Right, so this would be 1, then 2, then 3, right, then 4. That's the correct order for numbering. Okay, draw the mechanism for the formation of the following reaction. So this is acid chloride formation. We have our hydroxyl group. Remember, we're always going to draw our resonance. Then we have a nucleophile that's attacking the sulfur that's going to kick out electrons onto the oxygen. When those electrons come back down, they kick out the chloride. Alternatively, you could directly kick out that chloride. That too would be acceptable. Now you have this intermediate that the chloride attacks. Then we reform the double bond, kicking out the oxygen attached to the sulfur. That's a really great leaving group. When we do that, we can actually have the electrons come down to form a double bond and kick out the chlorine. Right? This chlorine can then serve as a base, which deprotonates the hydrogen associated with the oxygen, and that gives us our final product. So why does acetic acid boil at 118 degrees Celsius, whereas acetyl chloride boils at 51 degrees Celsius? We draw each molecule and indicate relevant functional groups and any relevant interactions. So this is my carboxylic acid. Notice how many hydrogen bonds I'm able to draw here. Whereas if I compare my acid chloride, I'm not able to draw as many hydrogen bonds. So it's really the intermolecular forces. So these are the forces that are between molecules that make the difference. Okay, in terms of drawing these molecules and relevant stereochemistry, in this case, my 3-oxopropanoic acid, the oxo refers to the ketone, the oic acid refers to the carboxylic acid. For the cyclohexane carbaldehyde, remember this carbaldehyde indicates that I have an aldehyde appended onto a cyclohexane ring. Drawing a reasonable complete mechanism and expected reaction products for the reduction. In this case, sodium borohydride is able to reduce, but it's only able to reduce some things, not all things. So in this case, it's not strong enough to reduce the ester. The ester will stay as it is, but it can reduce the ketone. By doing that, we have a hydrogen which has a lone pair and a negative charge. This is the hydride, so it's going to be my nucleophile. It's going to attack the carbocation, which is revealed when I draw the resonance structure for my carbonyl group. My H- attacks. I now have this negative charge on my oxygen, which can be protonated via any type of protic source, water, methanol, ethanol, isopropanol, and this should be done carefully because it can be exothermic, incredibly so, and so that generates a secondary alcohol. So how does the presence of water affect the following reaction? Well, in this case, water is going to be one of the intermediates. So this is a Fischer esterification. The presence of water will drive the equilibrium of the reaction back towards the starting material. So if I think about it, if I wanted to take an ester and convert it to a carboxylic acid, all I would need is water and an acidic source. So it's going to be very difficult for me to actually end up with very much of this product. So a byproduct of esterification is water. So I have to remove that water to ensure as much conversion to the ester as possible. You're actually going to do this in your lab when you do your fruity fragrances. Amines are functional groups frequently found in biochemistry as well. So the difference in reactivity between these two molecules, one is an amine salt, the other is the presence of a lone pair on the Lewis base or nucleophile. Remember that amines can react and actually generate multiple nucleophilic substitution products. So in this case, my nitrogen is the nucleophile, kicks out my bromide. I'm able to create an amine lone pair by having my base subtract that proton. And then, of course, if I have that lone pair, I can go through nucleophilic attack again. And I do that until my nitrogen is completely substituted with alkyl groups. So how does pH affect the behavior of amines and amino acids? So 3 examples. If we think about proline, that's one example. If we think about lysine, that's another example. If we think about histidine, that's a third example. Each of these are going to behave differently depending upon the pH with respect to their relative pKa's. Nucleophiles and electrophiles are hidden throughout biology, so you have to be able to label the electrophile and the nucleophile. In this case, remember, a double bond is always a lone pair in disguise. And then this Br2, these two bromides are not equal. One of them is going to function as an electrophile. The other then is going to function as a nucleophile, as shown. To draw a reasonable mechanism for the following reaction in all possible products, if I have a ketone and I have acid and an alcohol, I'm likely going to form a hemiacetal or an acetal. So in order to do that, I need to draw the resonance structure, then have alcohol attack. I'm going to transfer my proton over to create water, an excellent leaving group. And then my alcohol can attack, or my water can leave. Both of those are equally favorable, and that's going to generate my acetal. So what determines nucleophilicity or the strength of nucleophiles? So 3 examples. Nucleophilicity can increase as the charge on the atom becomes negative. Nucleophilicity can increase with basicity. Nucleophilicity increases with polarizability or size. So what amino acid can form disulfide bonds? This is going to be cysteine. Notice cysteine is a sulfur compound. What's not shown here are the lone pairs. Those are what are capable of forming this disulfide bond interaction. So for here, labeling acid base, conjugate base. So if I think about this, right, this is my acid. Why is it my acid? Well, because it's completely protonated. This is my base. When I generate my completely protonated species, that's going to be my conjugate base. My conjugate acid in this case, right, is just going to be water. Arrange them in terms of categories. Positively charged, neutral, negatively charged with respect to pH 7. That's pretty straightforward. The relationship between structure and function is significant. So drawing and labeling all functional groups. Being able to draw a reasonable mechanism for the following molecules. So this is the formation of an imine. Remember, you're always going to protonate with the acid first. Then you're going to have your amine attack the nucleophile, or your amine as the nucleophile attack your carbocation, the electrophile. Then you're going to generate water. Water leaves and your amine forms by the lone pair coming down and forming this iconic double bond. Remember, you have to do something with that positive charge. So likely your HSO4 minus will take a proton if that's available. But in this case, I can't do that. I can't do that because I have 2 methyl groups. So this is the most stable form of that compound. Why is it critical in Grignard reactions with carbonyl compounds to use ether and remove water during the initial reaction? Well, a protic source such as isopropanol has to be added carefully because it will quench. So essentially any remaining Grignard reaction will be quenched to form just the alkyl group itself, and as well as any leftover ions. Primary metabolites such as carbohydrates, so being able to label axial and equatorial as well as the anomeric carbon. So this is an example of an alpha anomeric carbon. Being able to draw the Haworth-Mills and chair configuration. So you're given the Fisher. I've indicated the anomeric carbon, and I've indicated what each of these structures look like. Why are both anomers possible? Well, they're possible because of mutarotation. So a cyclic hemiacetal can open to the linear form and then reclose again in the opposite direction. Remember, if it's up, that's beta. If it's down, that's alpha. Okay, let's take a look at the other practice problem. So name the following compound, number each carbon, identify any relevant stereochemistry. So in this case, we're naming acids. So 1, 2, 3, 4, that's S2-methyl-3-oxybutanoic acid. The mechanism for the deprotection of the ester. So in this case, I'm taking off this OCH3 group using acid and water. So I'm going to protonate, and then water is going to attack. I'm going to transfer a proton to create a better leaving group. My alcohol leaves. As my double bond is formed, I'm going to deprotonate this acidic proton, and now I have my carboxylic acid, H2SO4, and methanol. Consider diethyl ether and 1-butanol, for example, which are constitutional isomers with the formula C4H10O, which will have a boiling point of 34.5 degrees, which will have a boiling point of 117 degrees. Why? Well, if I look, the alcohol is capable of forming a great many more hydrogen bonds, whereas the ether is not. So that hydrogen bond donor and recipient compared to being only a hydrogen bond recipient. Drawing the following molecules, paying attention to any relevant stereochemistry. E4-hydroxy-pent-2-enal, so al means there's an aldehyde. The pent-ene means there's a double bond, and 4 refers to the hydroxy group. E refers to the stereochemistry about the double bond. 3-chloro-2-methylcyclohexene known. So again, a double bond, the chloride group at the 3 position, the methyl group at the 2 position, and then the ONE refers to the fact that it's a carbonyl or a ketone. Resonance, again, for my carbonyl compounds, that gives me the place where my hydride will attack. Remember, this hydride is a nucleophile, so it's H with a lone pair, which has a negative charge. That's what makes my nucleophile. The nucleophile attacks the carbocation. I then will protonate and regenerate my hydroxyls. Of course, right, those hydroxyls can come down, one of them, and form the aldehyde. But again, this aldehyde can also be reduced by a second equivalent of hydride to generate both a primary and a secondary alcohol as the final products. If we think about the presence of water for the following reaction, a likely byproduct is simply the quench, right? So it's to generate just the carbanion, forming the methyl instead of the product. Difference in reactivity between 2 nitrogen functional groups in glutamine. One is an amide, the other is an amine, a basic nitrogen versus the resonance form of a carbonyl. If you were to draw a reasonable complete mechanism for the formation of an imine, you can actually see that process here. Again, the nitrogen attacks the carbocation. The electrons are transferred from acidic hydrogen to form water. Water leaves, and the lone pair comes down to form a double bond. How does pH affect the behavior of carboxylic acids? So at least 3 examples. So this is aspartic acid. There are actually 3 pKa's, the carboxylic acid, the R group, and the ammonium group. And again, each of those pKa's, once our pH rises above that pKa, then we're going to deprotonate that proton. Label the electrophile and the nucleophile for the following reactions, as well as drawing the intermediate. So we have a nucleophile in disguise. We have our electrophile. And note again, we're going to generate a carbocation, which is our electrophile, and then water in this case is our nucleophile. To draw a reasonable mechanism for the following molecule, this is an oxidation reaction, so the oxygen attacks the chromic acid. We have a base which takes the proton, transferring the electrons to the oxygen, and then we have another base that deprotonates, and the electrons from that bond form the double bond, kicking out to form our leaving group. And this is what we would call a Jones oxidation. So what determines nucleophilicity or strength of the nucleophiles? So all nucleophiles are Lewis bases. lone pairs, and negative charges are very common. And the faster the reaction rate, the stronger the nucleophile. So we're thinking about things like charge, electronegativity, solvent, and then any steric hindrance. So we remember that sterically bulky groups are terrible nucleophiles. Oxidation and reactions are critical reaction mechanisms in biochemistry. So when we think about pKa's, it's important for us to know what that means. So in this case, we've indicated aspartic and glutamic acid and the fact that they have 3 pKa's. We've indicated lysine and arginine and histidine, and also tyrosine. So if we think about the acid-base reaction of glutamic acid and sodium hydroxide, these are examples of deprotonations that could occur. And then for all the amino acids you know so far, are groups that could act as moderate nucleophiles. These are just a few to name. Note, it would depend upon the local pH, so lysine would have to be fairly basic before it would function as a nucleophile. You should expect to have to draw all functional groups. That's a guaranteed question, I think, on this next exam. Being able to draw a reasonable mechanism for 4-hydroxypentanol in a solution with trace acid, where any water formed is removed. It's going to show you the formation of, in this case, a hemiacetal. Water can function as both an acid and a base. These are 2 examples that you could use. So when it's an acid, it will be a proton donor. When it's a base, it will be a proton acceptor. And of course, you've seen this before. It's going to show up again. So this is labeling axial and equatorial as well as the anomeric carbons. This is drawing Haworth, Mills, and chair configurations, and then a mechanism for the formation of the cyclic hemiacetal. There are a couple of examples of errors that are common to see. So in this case, we've lost a hydrogen. In this case, we've drawn too many electrons. In this case, we use arrows to indicate that it's resonance, but in fact, it's not resonance. It's actually tautomerism. So going back and forth between keto and enol are actually isomers, not resonance structures. Thanks again. Have a great day, and we'll catch you next time.